change of variables. Very important to understand each and every step. Suppose phi is a strictly increasing continuous function that maps an interval, closed interval capital AB onto closed interval small ab. Suppose alpha is monotonically increasing on this closed interval small ab and f is Riemann integral on alpha on this closed interval small ab. We define beta and g on closed interval on capital AB by beta of y is equal to alpha of phi y and g of y is equal to f of phi y. Then g is Riemann integral on beta and integration from a to b g d beta is equal to integration from small a to b f d alpha. This we have to prove. Now what is given to us? We have given one phi function which is strictly increasing and is continuous function, which is mapping interval. It is a map on this closed interval capital AB to closed interval small ab, right? Which means, and it is also your onto function. Now what is the meaning of the onto function? That is every element of the function's codomain. This is codomain and this is your domain. Now every element of the function's codomain is the image of at least one element of its domain. So for every element in this codomain, there must exist one element in its domain, right? For onto map. Now phi is onto map, which means if I take any element y from this closed interval, then what are the elements supposed to be in this set? Phi of y. And second thing which is given to us is that we are given two functions which is again defined on this closed interval capital AB. One is beta and one is g. These two are also defined on this interval. If beta is defined, what is the definition written over here? Beta of y. Again, if I am having any y element over this, then beta of y will be equal to alpha of phi y. Obviously, the elements present in this codomain is like phi of y, right? So how beta is defined as? Beta of y is equal to alpha of phi y. And g of y is equal to f of phi y. Now f is another function which is Riemann integral on this closed interval small ab, right? So for here I am having the function f, and for this side I am having the function g. If here I am having the function alpha, then on this side I am having the function beta. So for f I am having g, for alpha I am having beta. Fine? Alright, let's start the theorem. The proof is very easy. Let me start with the function phi. Since phi is defined on this closed interval capital AB, which is mapping this to closed interval small ab, and this is onto. So therefore, let me take a partition P from this closed interval small ab. So to each partition P equal to x0, x1, x2, so on xn. This is a partition for this closed interval AB. So here partition is P. So to each partition P, there corresponds a partition Q of this closed interval capital AB. So let me take this partition as y0, y1, y2 up to yn, such that now for every element of this xi, right, because I'm having the partition P over here and elements are like x0, x1, x2. So for every xi, I'm having at least one element in this from this closed interval, that is phi of yi. Simple? Right. Because here Q is defined to be as a partition and elements of Q are like y0, y1, y2. So for every element xi, there exists element yi such that xi is equal to phi of yi. The definition for the onto function. Now all partitions of closed intervals small ab are obtained in this way. Now what is given to us according to the definition? It is given to us that g of y is equal to f of phi y, right? So g of yi is equal to, yes, what will be the value? Is equal to f of phi yi. And further this is equal to, because phi of yi is xi, so this is f of xi. Right? Okay. Now the another definition. What is beta y given to us? Alpha of phi y. Let's use this definition. Beta of yi should be equal to then alpha of phi yi, which is equal to alpha of, instead of phi y again it is xi. Simple, right? For all I less than equal to n and greater than equal to 1. Here also, for all I less than equal to n and greater than equal to 1. What is happening over here? The value of f at partition P is same. The value of f at partition this P is same as value of g at partition Q. The value of f at partition this P is same as the value of g at partition Q. Here I am having, here beta and g are defined, and here alpha and f is defined. This is Riemann integral, right? So we got this result, right? So therefore the values taken by f on closed interval xi minus 1 xi are exactly the same as those taken by g on yi minus 1 yi closed interval, right? So thus u, q, g, beta will be equal to, now the upper sum of this partition q on g beta, this will be equal to upper sum of partition p. Yes, instead of g I will write, what I will use over here? Yes, f. And instead of beta I will be having alpha. Is the difference clear? Alright. Similarly, the lower Riemann sum for the partition q, g, beta will be equal to lower Riemann sum for the partition p, f, alpha. Let me mark this as 1. So values of f at partition P is same as the values of g at partition Q. Now third thing given to us is that f is Riemann integral on alpha. So let epsilon positive be given. Since f is Riemann integral on alpha on closed interval small ab, so therefore there exists a partition P of closed interval ab such that UPF alpha, this is the result, minus LPF alpha is less than epsilon, which implies, now instead of UPF alpha from 1 I can write UQG beta minus LQG beta is less than epsilon, because these are exactly the same, right? Okay, but epsilon was arbitrary, so which implies G is Riemann integral over beta on closed interval capital AB, and integral from A to B G d beta will be equal to then integral from small a to b f of d alpha. That's it. What is going on is just the change of the variables, right? So it is very important to understand this result. Thank you so much for watching this video. Next time we are going to work on with the new topic, on Riemann Stieltjes integral, and that is the integration and differentiation. Thank you so much. God bless you.